All right, so we're gonna start here with notes number 39. We'll keep going from where we left off right before spring break, right, where we covered the dividing complex numbers. So graphing complex numbers will be what we touch on first. All right, so I want you to kind of notice something here, that there is this graph, and so you really only need maybe like two boxes. You don't need more than that, because what we're gonna do is just I'm gonna plot everything on the same axis, just to kind of show, you know, how everything goes. You don't need to copy this over and over. Okay. All right. Got a couple people coming in. Cool, cool, cool. All right. Okay. So, all right, got a couple more. All right. So the first thing here is let's talk about what the complex graphing complex numbers. Basically, what is the name of this new axis? So if you take a look at the image over here, whoops, I don't want that. Hold on, let me erase this. Don't want this. Okay. Notice how it's very similar to the XY axis, right? You have your real. The only difference now is that where the x-axis used to be, that's now the real axis. And then where the y-axis used to be is now the imaginary, right? So I want you to think about them in that sense, right? That you have your x-axis, well, that's your real axis. And then your y-axis is the imaginary axis. Okay, so that's why you see that the numbers across the x-axis, those are whole numbers. Well, not necessarily whole numbers, but they're real numbers, right? They don't have the imaginary I, right? Versus the numbers that are on the imaginary axis do, right? So you have your 2i, your 4i, your 6i, your 8i, your 10i, right? So they basically grow in the same way that they normally do, right? But if you are on the y-axis, then you're an imaginary number, okay? So here's what we're gonna take. Here's what we're gonna do. So all you really need to do is just sketch out one of these, and then I'm just gonna put a series of imaginary numbers or complex numbers on the first box, and then we'll go ahead and we'll just plot them. We'll talk about how to do that. Okay, so we're gonna go ahead and graph. First of all, let me give you the name for this new plane. So it's not really the XY plane anymore. It's something that could be called the complex plane. You could call it the complex plane. There's also another name for it. Sometimes it's called the Gauss plane. So Gauss is he's a really old mathematician. He spent a lot of his life working on complex numbers. There's a whole field of study in math for complex. I took a class in college, a whole semester just of complex numbers. Pretty crazy, pretty interesting class. Okay. All right, so when we graph these, we're going to start with a couple of complex numbers. So let's go ahead and list them off. So we'll call this complex numbers 2 plus 3i. We have B. We're going to call that -4 minus 5i. We have C. -3 plus 4i. We have D. 10 plus 7i. We'll go with E, which is 7. And then in comparison to that, then we'll do F, and we'll do 7i only. Okay, so it's really simple how to graph these. You want to think of them as coordinates. You want to think of them as coordinates. So how are they split up? Well, if this was a coordinate, right, you would have a 2, comma, well, that's a 3i, positive 3i, so 2 comma 3i. Right, so where is that coordinate? Well, so then you would travel 2 units along the real axis, 1, 2, and then you would go up 3 units on the imaginary axis. So 1, 2, 3. Okay, so you would put a point right here. And this, you could call it your A, right? That's the point that represents the complex number 2 plus 3i. Okay, so because it was a positive 3, that's why we went up. Had it been a negative, then we would have gone downwards. Okay, let's do B real quick. So B, -4, that's my X, I'm sorry, that's gonna be along my real axis. So -4, comma, and then because I have a -5i, then that means I'm gonna use -5i as my imaginary. So move 4 units to the left and then 5 units downward. Okay, so you're gonna have a new coordinate down here, and we can call that B. Okay. Let's do a few more. For -3 plus 4i, that means that the real value is -3, but the imaginary value is a positive 4i. Okay, so that's our coordinate. Okay, so now we can say -3 to the left on the real axis, and then up 4 because it's a positive 4, so we go up. And we can put a point right here. Okay, and we can call that point C. And you get the idea, right? That's pretty much all graphing is about. It's literally just take the real number and the imaginary number, you split them up as a coordinate, and then you plot the point. Okay, so let's keep going. Let's do D, right? So that's a positive 10. So positive 10, and then a positive 7i. Okay, so we're gonna go 10 on the real axis all the way out, and then up 7i. So I believe that's right here. Okay, call that point D. And then E, right? What happens if you only get a real number, right? There is no imaginary number there, right? It's only a real number. So then you would go along the real axis to 7, right? But because you don't have an imaginary number, that means you don't go up and you don't go down. You're going to stay on the real axis. So your point is just going to be at the 7 there. Okay, so that's your point E. Okay. And then the opposite is if you would have had only imaginary, right? What if it's only imaginary? Well, then you're not going to travel anywhere on the real axis. Okay, you're not going to go left or right. You're just going to move vertically. So in this case, because it's a positive 7, you're going to move up to 7 and put a point there, and you can call that point F. Okay. And that's really all that there is to it for graphing. It doesn't get any harder than that. That's literally all that it's about. So it's a really easy thing. It's just introducing the complex plane as real and imaginary instead of X and Y. But you can treat it the same way. It's very, very similar to the original X and Y axis, okay? Are there any questions about the graphing? How do we feel about that? Are we okay? Are we good? Okay. All right. Okay, so if there's no questions, then let's move on because that's pretty much it for notes number 39. Okay. So let's go ahead and let's move on to notes number 40. So, excuse me. So for notes number 40, here's the title. Go ahead and make 6 boxes. We're calling it solving quadratics using square root. So we've done a little bit of this. The only difference now is we're going to solve quadratics that may have imaginary solutions. Okay, so that's the only difference. So when we know how to solve them with imaginary solutions, we can solve any quadratic. All right. So I'll give you some time to go ahead and set up your notes. And just 6 boxes for today. Okay, so there's our first example. And so, we're going to approach this the same way that we did in the past. Okay. So the idea here, the methods we want to use is to use square root, right? We know we could probably expand, right? We could expand the x minus 2 squared and then maybe try to factor, but we don't want to factor, right? Specifically, we want to be able to use the square root method. Obviously, you can use both if you were ever in another situation, but sometimes the square root method is a little bit easier than trying to factor, right? It's a lot less steps usually. Okay, so then, we're looking at this equation. Always identify how many solutions you're supposed to get, right? That's the part where when you're dealing with quadratics, you're looking for typically 2 solutions, all right? So don't forget that. So when I apply a square root to both sides here, right, that's the method that we use to eliminate the square, right? That's going to help us eliminate because they're inverse operations. So then we get to bring down the x minus 2. Okay, now in this case, okay, I'm left with the square root of 5, right? We can't take the square root of 5 in this case because 5 is too small. It's a prime number, right? So if you were to try to do a factor tree on 5, just imagine you're stuck with 1 times 5. There's no pair. There's nothing you can do to simplify. So then what is your answer? Well, your answer is the square root of 5. The common mistake that I see sometimes with students is that they'll take the square root of 5 and then down here they'll put 5. Right? You can see why that's wrong because the square root of 5 is not 5. The square root of 25 is 5. So just be aware and to not forget to bring down. Sorry, I'm having eraser issues. Not to bring down the square root with it. Okay, now, what's the issue? What needs to be brought down in addition to the square root of 5 if we're supposed to end up with 2 solutions? And then feel free to share. Plus or minus, maybe? Yeah, that's what we need. Okay, so we need a plus or minus here because then that helps account for the 2 different solutions that we're looking for. Okay, all right, so from here, check it out. You're gonna have to split this into 2 equations, one utilizing the positive square root of 5, one utilizing the negative square root of 5. So you have x minus 2 equal to square root of 5, right? We'll consider that one the positive. Then we have x minus 2 is equal to the square root of is equal to the negative square root of 5, okay? All right, here's where then this gets a little bit tricky, okay? We're not going to approximate this. You're not going to turn this into a decimal. What I want you to do is to leave it as an exact answer, which means that you're going to leave it in square root form. Now, the thing is that we need to get x by itself. So in order to get x by itself, you need to add 2 to both sides. Okay, now when you add 2, okay, you're not adding 2 to the inside of the root. Okay, you're adding 2 to the value of the square root of 5. Okay, so it would be incorrect to then all of a sudden change that to square root of 7. It's just not possible. What you're allowed to do is say that this is equal to 2 plus root 5. Okay, that is your solution there. Okay, 2 plus root 5. On the other end, okay, on this side, you add 2 as well. The 2's cancel, and you're left with x is equal to 2 minus root 5. Okay, and these 2 represent your exact answers. Okay. Are there any questions there? We okay so far? All right. Okay, then let's move on to example 2 then. Okay, so on example 2, okay, somewhat similar. Let's practice a little bit here. We have x plus 3 squared all over 4 is equal to 8. All right. So again, right, we're trying to isolate the x plus 3 squared. We want that alone because then we can apply the square root. So the first thing we ought to do here is first get rid of the 4 in the denominator, right? In order to do that, we can multiply both sides by a 4. That's going to help us eliminate the 4. Now we can bring down the x plus 3 to the power of 2. This is what we want, right? We want this expression isolated because now we'd be ready to take the square root. You don't want to take the square root at the very beginning because now you're going to have to deal with taking the square root of the numerator and the square root of the denominator. It's going to get messy, okay? So remember to leave the square root almost like till the end, okay? Until everything else is cleaned up. All right, now on the other side, 8 times 4, that's going to give us a 32. Okay, now we're in a position where we can apply square root. So let's go ahead and do that. All right, so what happens? Square and square root, inverse operations, they cancel each other out. You can bring down the x plus 3. Now, square root of 32, while you could bring it down, remember that you can simplify some of this. Okay, so 32, if you turn it into a factor tree, think about what those possibilities could be. I know that 32, a nice one is 16 times 2. And the reason why that's a nice one is because then we know that 16 is the same as 4 times 4. Okay, so then when I look for a pair, I have a pair of 4s, and then the 2 is by itself, right? So we box the 2, that goes inside the root, and the 4 goes on the outside. Okay, so what is the new expression? The new expression for root of 32 is the same as 4 root 2. Okay, now remember that you're solving quadratic, you need 2 solutions. So don't forget the plus or minus. The plus or minus goes in front of the 4. Okay. Any questions on that part so far? We okay? All right. Okay, so now next part would be, we can split this up, or, okay, instead of splitting it up, because we know that we're still going to get those 2 solutions, here's what we can do instead, all right? It's kind of like the shortcut. Rather than going back and here, you see how I had to split this up into those 2 equations. Actually, no, not down there. Right, I had to split it, right? And then one was positive, one was negative. But then notice how here my solution was like 2 plus root 5, 2 minus root 5. That's essentially the same thing as saying 2 plus or minus root 5, right? Because you can still use those 2 options. This is another very valid way to write your solution. I'm going to try to do something similar on the other side to save some time and to save some work. Okay, so notice how in order to get the x by itself, what do we need to do? We have to subtract 3 from both sides. Okay, so I'm subtracting 3 from both sides. Now, the 3 cancels, x is equal to. All right, again, this is another one of those tricky things with square roots where you are not allowed to combine the coefficients unless, right, unless they both had the square root of 2. This goes back to the other lessons where we talked about. They need to have the same term, which means that they both need to have square root of 2 if I'm going to be able to combine the coefficients. But in this case, 3 doesn't have a square root of 2. So there's no way I can combine it with the 4. So here's how we leave it. We're going to leave them separate. You're going to use -3 first. And then what comes after is plus or minus the 4 root 2. So those 2 values stay separate from each other. All right. We cannot combine them because they do not share the root 2. Okay. So they're basically not like terms. So we have to leave them as separate. Okay. Does that make sense? Let me know if you have any questions about that. And of course, if you don't want to, you can always send me a private chat and let me know, like, hey, can you go over that one more time? If you don't feel too comfortable. Okay. All right. So that's kind of the way that I want to go ahead and leave these solutions, because they basically mean the same thing as having one solution that says x equals -3 plus 4 root 2 and -3 minus 4 root 2, right? It's already basically built in where I have the positive and the negative version, but it's a condensed way of writing my solution, okay? And we've kind of seen that before where we might leave it as like x equals plus or minus 2, okay? We've done that, all right? Okay, so far, right, solving using square roots and no imaginaries have come up, right? So these are still dealing with solutions that are real. If we were to graph these solutions would show up. they would have intersections on the x-axis, right? So that's how we know we're in a good spot. But then what happens once you start dealing with negative, right? Negative inside the square root. Well, that's all of the 2 weeks, 3 weeks that we've spent converting them into imaginary numbers. Now we're going to be able to do that as well. And we're still going to be able to get some solutions algebraically. All right. Okay, so now for example 3, let's take a look at this one. So we have 5x plus 4 quantity squared is equal to negative 36. All right, so let's see what we can do with this, okay? First of all, there's no terms on the outside of the parentheses that we need to get rid of first, so we can just go ahead and apply the square root, right? So if we apply the square root on both sides, then I didn't notice here that the square and square root cancel. We can bring down the 5x plus 4. All right, now on this side, what can we say? Right, notice how you have the square root of a negative 36. So if you were to make that conversion, right, just do a little bit of an aside scratch work, that's like saying the same thing as the square root of 36i, right? Now, the square root of 36i, well, square root of 36 is just 6, so it's just 6i, okay? But here's where you have to be really careful and not to forget the plus or minus, all right? Because if you only brought down 6i, you would only eventually end up with one solution, which is not what you want, all right? You want 2. So make sure you bring down plus or minus 6i, okay? All right, from there, what we're trying to do is remember to isolate the x, okay? We gotta get x by itself. So here's what we can do next. Subtract the 4 from both sides. And now you're left with 5x is equal to, notice how one number is a real number, 4 is a real number, and 6 is imaginary. So those numbers do not mix, okay? So you need to write this out as negative 4 plus or minus 6i, okay? Then in order to get the x by itself completely, you divide 5 on both sides, which means you divide 5 to everything, okay? 5 cancels, now x is equal to, now you see why I split it up as I divided 5 to each individual thing. The reason why is because I know that eventually I need to write this in standard form of a plus bi. So I want to then have, right, my denominator is kind of separated so that I know exactly what my a is, I know exactly what my b is. So then I can go ahead and just bring this down. X is going to equal negative 4 over 5 plus or minus 6 over 5i. Okay, and then that represents the 2 different solutions there, the 2 different imaginary solutions. All right, that's where the 2 solutions come from. One would be negative 4 over 5 plus 6 over 5i, and the other would be negative 4 over 5 minus 6 over 5i. All right, and then that's what we get for our 2 solutions there. Any questions so far? How are we doing? My wife said I'm doing terrible. No. It's because she doesn't understand any of it. I'm kidding. I'm kidding. My wife is really smart. She's a nurse. Okay. Shout out to all the nurses out there. All right. Let's move on. Okay. Let's see. Anybody on the chat? Nothing. Shots fired. Shots fired. Yeah. It's gonna be a tough day in this household. All right. Example number 4. Let's see what we have here. All right. So example 4, something similar. Let's take a look. Let's try this one here. Okay. So 4 times 2x minus 3 to the power of 2 is equal to negative 100. Okay, so something important about the algebra here, remember that you cannot distribute the 4 because the power of 2 takes priority. Okay, so that means that you need to first isolate the 2x minus 3 to the power of 2, okay? Do not distribute the 4. So we go ahead and divide both sides by, oops, don't want that. Divide both sides by a 4, all right? That's gonna cancel this. And here's what you're left with is a 2x minus 3 quantity squared is equal to negative 100 divided by 4 is gonna give us negative 25, okay? All right, so now next, now you can apply your square root, both sides, okay? We're gonna get something similar to what we got in the previous problem in example 3, okay? So we wanna keep working through this. Square root and square cancel, and you're left with a 2x minus 3 is equal to, well now here, this is where you can do your little side scratch work. Square root of negative 25 becomes square root of 25i. And then the square root of 25 is 5. And you can bring down your I, right? So now you have 5i. And then don't forget here that you're solving for two separate solutions. So you need plus or minus 5i, okay? All right, let's get x by itself, okay? So now we want to add 3 to both. Again, this is a real number plus an imaginary number, so you do not combine those coefficients. What you're going to leave it as is 2x is equal to 3 plus or minus 5i, okay? Leave it in standard form, okay? Now we go ahead and divide both sides by 2. Divide every term by 2, okay? Because then it leaves it in standard form for you. You don't have to combine it and then separate it again. So now your final answer here is going to be x is equal to 3 over 2 plus, I'm sorry, plus or minus 5 over 2i. And there are your solutions. Okay. How are we doing so far? I'm guessing we're good. Okay. Yep, okay. Yes. All right. All right, cool. Cool. Okay. All right, now the last two, let's take a look. Similar difficulty, just, slightly different approach. All right, so let's start here. Example 5. So we have 1 over 2 z plus 1 quantity squared equal to negative 18. All right. Okay, so again, my parentheses squared is already isolated. There's no terms on the outside that we need to get rid of. We can go ahead and jump in by applying the square root to both sides. Okay, square and square root cancel. We can drop 1 over 2z plus 1, and that's going to equal. And then here's where we have to spend a little bit of time cleaning this up. Okay, so we know square root of 18 becomes square root of 18i. Now we also have to clean up the square root of 18. You don't want to leave it like that, especially if you can break it down any further. So 18 as a factor tree, you can break that into 9 times 2. And then 9 becomes 3 times 3. So now you have a pair of 3s and then a 2 that goes back inside the square root. Okay, so really square root of 18 is actually 3 square root of 2, and then you drop the I. Okay, so what does that mean for us? That means then we bring this value back into the equation as 3 root 2i. And then of course, don't forget here, you apply a plus or minus. All right. Okay, so now let's go ahead and isolate z as best as possible. Okay, so we want to first subtract 1 from both. Okay, so we have 1 over 2z is equal to negative 1 plus or minus 3 root 2i. Okay, again, we're keeping the negative 1 separate from the other coefficient because one is real and the other is imaginary. So there's no way we can combine those. All right. And then here's what we can do. Okay, now I need to get rid of this 1/2, right? So in order to get rid of a 1/2, we can do the inverse and multiply by 2. Okay, so we're gonna multiply 2 to both sides. So I'm gonna wrap this in parentheses. We're gonna multiply by 2. All right, so now if I multiply by 2 here, these 2's cancel, we can bring down z. Now the rest, distribute the 2. Okay, so now when I distribute 2, 2 times -1 would be -2, plus or minus 2 times, guess what you're gonna multiply it with? You're gonna multiply it times the coefficient, or you're gonna multiply it to the inside of the root. Okay, if you said to the coefficient, you're right. Okay, you don't multiply numbers on the outside to the inside of a square root. You can multiply the coefficients together, 2 times 3. Okay, so that's gonna give you a 6. Okay, 6 root 2 I. Okay, and so then there we go. Those are our two solutions, the -2 plus 6 root 2 and the -2 minus 6 root 2. All right. Any questions on that one? We okay so far? All right. Okay, all right, so last one. Let's take a look at example 6. Okay, so example 6, we're looking at 3 times 5 minus x to the power of 2 plus 1 all over, this entire expression, all over 4 is equal to 7. Okay. All right, so this one's got a lot of algebra to it in terms of first trying to isolate the 5 minus x squared. Okay, that's the big thing, is that we can't apply square root until the 5 minus x to the power of 2, until that's by itself. Okay, so first thing is, since everything has a denominator of 4, first get rid of it, right? So kind of like fraction bust it, multiply everything by a 4, or multiply both sides by 4. So here, this 4 will cancel out with this 4. So you can then bring down 3 times 5 minus x quantity squared plus 1 will equal 28. Okay. All right. From here, right? We should get rid of the 1 first. Okay, so subtract 1. 3 times 5 minus x squared will equal 27. And it looks like something kind of friendly, right? I don't think we're even going to get imaginary out of this. Okay, so divide both sides by a 3 now. Okay, get rid of this 3 so that you can then apply the square root after. And you're going to be left with a 5 minus x squared equal to 9. Okay, 27 over 3 is 9. All right, so we're ready to apply that square root. Get rid of the square. Apply the root to both sides. So now square and square root will cancel, and you're left with 5 minus x. And then that's going to be equal to 3, right? But don't forget that since you're solving a quadratic, you need a plus or minus to be able to get your two solutions out of it, okay? All right, so now here at this point, depending on your comfort level, you can choose to split it up, or you can choose to try to solve it all through at once. Here, let's first subtract the 5. So I'm going to subtract 5 here. Okay, so here's how you can set it up, right? So now you have negative x is equal to, you have the -5. I'm going to leave it like that for now, and then plus or minus 3. Okay, this is probably where one of those situations where you might want to split it up just to be a little bit more comfortable, because notice how x is not by itself. You have a negative there, right? So if you're not sure like how to approach this, then just simply split this up into the two different equations. You have negative x is equal to -5 plus 3. And then you also have negative x is equal to -5 minus 3. Okay? So on one side, you have negative x is equal to negative 2, which means you can divide both sides by negative 1, and x is equal to 2. On the other end, you have negative x is equal to negative 8, but if you divide both sides by negative 1, then you get x is equal to 8. Okay? And that's it. Okay, that's pretty much it. So any final questions on today's lesson or lessons? We okay? All right, guys. Well, then in that case, if there's no further questions, then I'll go ahead and I'm going to go ahead and log off. I will post these notes and I will then upload a video as well. For those of you who maybe joined a little late, or if, tell your friends, let them know that the video is available for them to catch up and watch the notes. I'll post a homework worksheet. If it's not a worksheet, then it'll be an IXL. Okay, so I'll let you. I'll keep you posted when I make a little announcement. I'll post something letting you know whether it's going to be homework 5 or if it's just an IXL to do for this. Okay. All right, guys. Well, it was good to see you. I'm glad you guys